Chapter 13 discusses benzene and its derivatives. It mentions that we have described so far 3 classes of hydrocarbons in our organic adventure together. It's alkanes, alkenes, and alkynes, collectively called aliphatic hydrocarbons. We know that alkanes had single bonds, alkenes had the double bonds, and the alkynes had triple bonds. But collectively, they are all known as aliphatic hydrocarbons. However, chemists began to realize that there was yet another class of hydrocarbons, properties that were very different from any of those studied thus far. Because some of these new hydrocarbons that were classified had pleasant odors, they became known as aromatic compounds. Aromatic compounds simply referred to any structure that had a benzene ring as part of its structure. Of course, the more and more of these aromatic compounds that were found, the more we realized that not all contained pleasant odors. Some of them had no odors at all, and some of them to have just downright unpleasant odors, especially if those that contain sulfur in them. But we already had classified them as aromatic compounds, but we just broadened that definition then to include aromatic compounds. Don't necessarily mean they have pleasant odors. It means that they contain benzene-like rings. The questions that we'll tackle in this chapter will include: what exactly is the structure of benzene? How do we go about naming these aromatic compounds? We'll study some characteristic reactions of benzene along with their reactions of its derivatives, and we'll study a special class called phenols in our final structure. These aromatic compounds we can see are hydrocarbons that contain benzene rings, and benzene is a structure that is cyclic, that has alternating 6 carbons in a cycle and alternating double and single bonds, and we'll talk more about that when we refer to residence. And we use this term arene to describe the aromatic compounds. Just as our group derived from the removal of an H of an alkane was called an alkyl group, it was given the symbol R. We use the symbol AR to use any aromatic compound, an aryl group, arene, AR. Don't confuse that AR with the symbol of argon, the element argon. This is representing an arene, just as if we saw an R hanging off of the chain in our previous chapters, it was an alkyl group, a functional substituent group. This AR symbol is going to denote aromatic compounds. Alrighty. So when we start to think about benzene being the simplest aromatic compound, about 1825, Michael Faraday introduced the idea that its structure was very different than any other hydrocarbon studied so far. He had determined its molecular structure, its molecular formula, to contain 6 carbons and 6 hydrogens, an unusually low number of hydrogens compared to any other structure studied so far in the aliphatic group. Chemists argued for years and years and years how might this structure actually be put together, because they were noticing it was not behaving as an alkene. An alkene group had double bonds. So take a closer look here. Here's our 6 carbon membered. And notice that here's the double bond, single, double bond, single, double bond, single. So the chemists were very confused. Why wasn't this behaving like an alkene? Just to recall some of the chemistry from alkenes we were talking about, we had C, double bond C, and however, remember, so we have propene here. And if we reacted that in terms of a halogenation such as bromine, we saw that we would break that double bond and introduce bromine onto the structures. Bromination. Even though this structure, which is double bond, single bond, it did not perform this way at all. We could not get bromine to react with benzene, as you might predict if this were indeed double bonded like any other alkene group. So we knew something was very different. Benzene didn't behave in any of the fashions from those chemical reactions we studied in the alkene chapter. Benzene wouldn't react with HBr, with water and sulfuric acid catalyst, or even be hydrogenated with the surface of like palladium, platinum, or the other high metal surface catalysts we studied before. All of these reagents that normally add to a carbon-to-carbon double bond were not behaving in this manner. So one of the first people who proposed a structure was known as Kekulé. And this is a chemist who decided that the cyclic structure must be represented by these alternating double bonds throughout the structure, and he proposed this particular proposal in 1872. But the reason that this was a proposal is we just couldn't get these compounds to react in the fashion of an alkene. And so they kept studying and kept looking at ideas of how to talk about the structure of benzene that still described its correct chemical properties. And this is where Linus Pauling added on. Notice the year difference. We had gone through 1872 from the Kekulé structure, which just had alternating double bonds, but did not do a good job in describing its chemistry, until about 1930, when Linus Pauling really gave us a better, adequate description of the structure, introducing the concept called resonance. And resonance is a term that we have used before in inorganic chemistry and does a very nice job applying it here as well. When I think about the resonance structure of benzene, I'm considering what I want to have happen is that I'm going to have contributing structures that really is a blend of the two. So let's compare what we have just seen in the previous slide, where I have a six-membered ring, 1, 2, 3, 4, 5, 6, and I said it's alternating double bonds. Alrighty. But now consider in another structure. Boy, that's not very neat, is it? I'll try again. Trying to draw a 6-carbon ring, 1, 2, 3, 4, 5, 6, that's better. And versus where we place those double bonds. So when I count these between carbon 1, 2, 3, 4, 5, 6, we could have a double bond between carbon 1 and 2, between carbon 3 and 4, and between carbon 5 and 6. However, if I just keep the numbering the same to draw my point home, why did I pick carbon 1 and 2 to put the double bond? Why couldn't it be between carbon 2 and 3, 4 and 5, and 6 and 1? And I know we would number differently, but I'm just trying to say that the point is both of these are correct. That a hybrid structure better describes this particular compound called benzene than any structure by itself. Resonance is a hybrid structure. Benzene is not the structure on the left. It's not the structure on the right. It's a combination of the two structures together. Now remember, we learned that the longest bond between any two atoms is a single bond. A shorter bond is the double, and even shorter yet is the triple in terms of bond length. The more shared pairs, the tighter those atoms become. In terms of bond length, single bonds would be the longest and triple bonds would be the shortest. We might imagine, if we look at this structure of benzene, that between carbon 1 and 2 would be a shorter bond length than between carbon 2 and 3. We might imagine there's a shorter bond length between carbon 3 and 4 than 4 and 5, and so forth. What we noticed through experimentation is that all carbon-to-carbon bonds were exactly equal. Now, how do we explain that? There is no difference in bond length between carbon 1 and 2 to carbon 2 and 3. That the delocalized electrons inside of this structure were exactly in the same distance at any certain point in time. So a better structure that describes resonance is often seen by drawing a circle inside the benzene to delocalize those bonds at any particular time. That the distance between the carbon-to-carbon bond is somewhere in here. It's not quite as long as a single, it's not quite as short as a double, but it's between the two where we have the resonance length of our bond. We call each of these separate structures a contributing structure. To show the real molecule is a resonance hybrid of the two Lewis structures drawn, we position this double-headed arrow between them. It's not the one on the left, it's not the one on the right, it's the hybrid between the two. They are two contributing structures. Do not confuse resonance contributing structures with equilibrium. A molecule described as a resonance hybrid is not in equilibrium among the electron configurations of each of those contributing structures, but instead that molecule has just one structure. The one structure is a hybrid of the two combined together. A good analogy uses the color wheel. We understand that purple is not a primary color. For example, we know that putting blue and red together, we can make purple. You can think of a molecule being represented by resonance as being purple. At no instant in time is purple ever blue or red. It's always purple. It's a hybrid of the two colors together. A molecule described as a resonance hybrid is not sometimes contributing blue, it's not sometimes contributing red, but it is always a single structure at the same time, always purple. And where the bond lengths are always an equal length and not one or the other. Wherever we find resonance, we find incredible stability. The Lewis structure is more stable than any of the hypothetical Lewis structures that had been drawn before. This resonance structure described with incredible accuracy why we couldn't get any of these benzene structures to react as we did with alkenes. We understood because of the resonance stability that it would not react with HBr, with water, or with hydrogen as studied in the alkene chapter from before. We understand there's two contributing structures for benzene. These resonance structures are a hybrid between each one, and that the length of the carbon-to-carbon bond in benzene, for example, is midway between that of a carbon-carbon single and a double bond. It is exactly between the two as a hybrid. Now let's discuss how we name aromatic compounds. Aromatic compounds do involve a little memorization. Let's talk about the one substituent groups, monosubstituted alkyl benzenes. Most often these are named, even by IUPAC, as common names. Just as you meet a new person and have to remember their names, we're going to meet some new structures and we have to remember their names. I noticed in my first structure here, I have my benzene ring and an ethyl group coming off. This name, according to IUPAC, is named ethyl benzene. Remember that, ethyl benzene. And of course this would be known as carbon number 1, not part of its name, but anything else after that that would be coming off would be numbered from there. If indeed we recognize this as benzene, you might want to call it methyl benzene, but it's not. It's known as toluene. And again, it's just coming from common names that were so much in use before we understood the benzene resonance structure. It's now truly part of the IUPAC system. Toluene is the name given to the structure of benzene when it has a methyl group off of it. And another important one to remember, introduce yourself to and remember its name. Here is an ethene, E-N-E, an ethene branch coming off of a benzene cycle. Styrene is the name of that structure. Polystyrene Maybe you've heard of polystyrene, just in the fact that that's a foam cup. Polystyrene is a foam cup which you might put your coffee in. So we've introduced ourselves to ethylbenzene, toluene, and styrene. The IUPAC system also retained common names for the following compounds. Introduce yourself to them and memorize. Here is a benzene ring with the alcohol group coming off. The alcohol functional group OH is known as phenol. Here is a benzene ring that has an oxygen with a methyl known as anisole. Here is a benzene ring with an NH2 group, commonly known as amine, but now when it's off of a benzene ring, aniline. Aniline. Introduce yourself and memorize its name. Here is the functional group of an aldehyde. Off of a benzene ring, it's called benzaldehyde. Here is the functional group of the organic class of acids, C-O-O-H, benzoic acid. We have the alcohol and the carboxyl group, known as a carboxylic acid, benzoic acid. You might sometimes just see that as written up here in this functional way. And again, keep in mind, these were common names that became part of IUPAC. So they are indeed correctly named according to IUPAC with these common names, just the way it worked out with these benzene derivatives. The substituent group derived by loss of a hydrogen from benzene is called a phenyl group, C6H5, a phenyl group. So notice here I'm removing a hydrogen to create a place of attachment. So a phenyl group, if it's behaving as a substituent group off of a chain, a phenyl group, or pH. In molecules containing other functional groups, phenyl groups are often named as a substituent. For instance, I have carbon 1, 2, 3, 4, and here it's hanging off of a phenyl group. C6H5 is another way of just writing out in terms of a molecular form. C6H5, we have to understand that truly is the phenyl group hanging off. So 4-phenyl, 1-butene with that double bond. Notice this is a phenyl substituent group of cyclohexene. Still a 6-carbon ring. Notice there's just a single, there's just one double bond in here. So here's the cyclohexene. And of course it's hanging off of carbon 1. So 1-phenyl cyclohexene. When benzene is named as a substituent branch, it gets the name phenyl. It is not phenol, it's phenyl, Y-L. When there are two substituent groups occurring on a benzene ring, we see that there are 3 isomers possible based on the location. We could number the atoms of the ring, or we often hear in terms of a Greek prefix, ortho, meta, and para. Ortho given the symbol O, meta given the symbol M, and para given the symbol P. Ortho puts those 2 substituent groups right next to each other at carbon 1, carbon 2. Meta positions the substituent groups at carbon 1 and carbon 3. And para positions the substituent groups at carbon 1 and at carbon 4. Let's look at these names. COOH. On a previous slide, I said introduce yourself to it and get to know its name. COOH coming off of the benzene, we called it benzoic acid. That's the parent name of the structure, benzoic acid. It will have carbon number 1. Carbon number 2, I see the bromo functional group. We could call this 2-bromobenzoic acid, but most often you're going to hear the Greek letters OMP for positioning. Since they are next to each other, we would call this ortho-bromobenzoic acid, and now we know that they are next to each other in that cycle. Here we have two methyl groups at position 1 and 3. 1,3-dimethyl benzene, or M-xylene. M-xylene. Meta for position 1 and 3. Here in the far over here, we have the root word ethyl benzene, and based on the alphabet, chloro is in first place. 1, 2, 3, 4, position 1 and 4, so 1-chloro, 4-ethyl benzene, or simply para-chloromethylbenzene. Para-chloroethyl benzene, I misspoke. So this particular slide is introducing ortho, meta, and para. And you might have heard me say a new word here, xylene, and I'll talk more about that in a particular moment. When we have two substituent groups off of a benzene ring and they're both methyl, we're going to hear that called xylene. So I could just, let me give a quick note here, something good to add on. Under this structure, here's our benzene. If we see CH3, CH3, in position 103, 1 and 3, it would simply be orthoxylene. Both substituent groups are methyl, so we hear the common name most often. Or the third place we could put this at carbon 1 and at carbon 4, and we'd have that called paraxylene. Xylene is a common name given to a benzene that has two methyl groups as a substituent. Alrighty. So here we had benzoic acid with a bromine. Alrighty. Here we had ethyl benzene, where chlorine, based on the alphabet, was positioned first. Let's keep practicing naming IUPAC for benzene and its derivatives. Sometimes we have 3 or more substituent groups coming off of the benzene, and it gets a little more complicated, but not too bad. When we have 3 or more substituents that are present on the benzene, we specify them with numbers. Only when there's 2 substituents can we use ortho, meta, para. When there are 3 or even more substituents, we have to number them. If one of the substituents imparts a special name, then that name of the molecule as a derivative of that parent molecule is used. If none of the substituents imparts a special name, then locate the substituents, numbering them to give the smallest set of numbers, and we list them in alphabetical order, and the ending becomes benzene. This is where it becomes very important to just know by looking, is there a special name given back when we said introduce yourselves to these molecules and learn their names, because those become the ending if they're special. For instance, here I have a special name for a benzene with the NO2 coming off. Here we have CH3 and we have Cl. Do any of those impart a special name? CH3, NO2, or Cl? When I refer to special names, it was way back in the beginning when I said, introduce yourselves to these and memorize their names. Right here is the structure called toluene. Toluene is when we have a methyl group hanging off. Notice that this will get priority as the special branch, becoming the root word toluene. Because its root word toluene, that will become carbon number 1 when we name it. On carbon 2 there is a nitro, and on carbon 4 there is a chloro. we number them to give the lowest set of numbers, but based on the alphabet, 4-chloro-2-nitrotoluene. Look at this structure. Are there any substituents that would give the benzene a special name? Go back to the slide and I said introduce yourself to these and memorize. Here's one right here. These are common names of monosubstitute benzenes. If I have an OH hanging off, it's now called phenol. This becomes the branch of phenol. At carbon 2, 4, and 6, we have tribromo. 2, 4, 6, tribromo phenol. What's going on in the third structure? Any special branch that will give its root word. Well, here we have an ethyl group. The ethyl bromine, coming back to the slide that said ethyl benzene, here is our special name, and so it will begin with carbon 1. At carbon 2 there is a bromo, and at carbon 4 there's a nitro. Notice the alphabet takes priority. 1 is the ethyl, 2 is the bromo, and 4 is the nitro, but we list those substituents according to the alphabet we have all along here. 2 bromo, 1 ethyl, 4 nitrobenzene. 3 substituents named alphabetically, but notice that we get the root word from special names. Let me insert a slide here and we can try a few more before we go on to multicyclic structures. Let's draw together. Let's draw a 6-cycled, 6-membered ring, a benzene derivative here. I'll put an iodine, and over here CH3. We should name this molecule. Maybe pause, try a guess, and then just pause the video, and when you have a guess ready, let's listen to see if we've done it the same. Well, here I have 2 branches, 2 substituents off of a benzene. And what I notice is this particular grouping is special. By special, I mean introduce yourself and memorize its name as toluene. This will become carbon 1. At carbon 3, I have iodo. 3-iodotoluene is one possible correct answer. However, this is a substituent that has 2 branches, right? There's 2 substituent branches, so oftentimes we hear the ortho, meta, and para. So when I look at that in position 1 and 3, I know that is meta, iodo, toluene. Either answer. This one probably more common. Let's try another. We'll draw a benzene cyclic structure. Let's place a COO up here, COOH. How about a bromine here and here? Let's name this structure. Any of the substituent groups special, that would become part of the parent name. And indeed, you've recognized this group certainly is. It's one that we introduced ourselves and memorized the name. That's benzoic acid. That tells us that will become carbon 1. Didn't matter which way I went because I ended up at carbon 3, having the first substituent branch. Notice this has 3 substituents, so we cannot use ortho, meta, or para. At carbon 3, 5-dibromo benzoic acid. 3,5-dibromo benzoic acid. Let's try another. Draw a benzene. Let's put an NH2 group at the top and a Cl at the bottom. Name that molecule. Are either of those substituents special and will become the parent name? Absolutely. we introduced ourselves to aniline. This guy right here becomes part of the root name, aniline. It will position carbon 1, 2, 3, 4. We have two substituent groups at place 1 and 4, so we could name this para-chloro aniline or 1,4-chloro, no, we don't need the 1, just simply 4-chloro-aniline. We don't need the 1 because aniline is always given position 1. Para-chloroaniline or 4-chloroaniline. The more we do, the more efficient we become. Let's draw another. Give myself some more room. We'll draw a benzene ring. Let's put an OH group at the top. And let's draw a nice funny looking one. To me it looks like snowman hands. Name that molecule. Well, do you recognize any that would become the parent name? And certainly we do. The OH is the parent name. And do you remember? Phenol. So that begins position 1. We introduced ourselves to that molecule earlier here, phenol, nomenclature to remember. And now we're practicing using those. With our structure, phenol become the last name. Carbon 1, 2, 3, 4, 5, 6. Now remember, even though that looks funny, there's actually 4 carbons in this substituent group, right? Carbon 1, 2, 3, 4. Do you remember the name of this funny group? 1, 2, 3, 4. And 1, 2, 3, 4 carbons there. This carbon has 3 carbons attached to it. It's a tertiary group, isn't it? Tertiary is given that prefix tert. Tert-butyl for the 4 carbon rings. So we have tert-butyl is really becoming part of that structure. Where are they located? Well, we have at carbon 1. No, we don't, sorry. Carbon 1 is the OH. At carbon 2, at carbon 4, at carbon 6. 2, 4, 6. And I needed room for a tri in there. So let me start over. 2, 4, 6, tert, but there's 3 of them, correct? So we hear tri-tert-butyl. That prefix is in there telling us at position 2, 4, and 6, there's 3 tertiary butyl substituent groups coming off of the root word phenol. Here is the IUPAC name for the funny structure we just drew. 2, 4, 6, tri-tert-butyl phenol. How about 6-membered ring? Let's put an NH2 group at top, a chlorine, and down here. Name that structure. Do you see a functional group that is special and will become part of the parent name? I do too. It's this one. That will get position 1. Do you remember what we named it? You're trying to introduce yourselves, memorize these root words. It's aniline. Aniline, the NH2 amine group coming off of a benzene. At carbon 2 and at carbon 4, dichloroaniline. There's one more on your page we might as well try. A benzene ring. Top position, let's put a COOH, C-O-O-H, and position here, NO2. COOH COOH, C-O-O-H. Sometimes you see it written C-O-O-H. That's a bond. C-O-O-H. What do we notice? That's a parent group that we're learning the name. We've introduced ourselves and memorizing its name, benzoic acid. At carbon 3, we have a nitro functional group. 3-nitro benzoic acid, all one word. 3-nitro benzoic acid. However, what's more common? A benzene that has 2 substituents at position 1 and 3, you'd probably see this written as M-nitrobenzoic acid. Meta is position 1 and 3. Ortho, meta, para. Those prefixes, the Greek little prefixes for ortho, meta, para, to tell us positioning. The last slide talks about polynuclear aromatic hydrocarbons, PAH for short. Polynuclear aromatic hydrocarbons are those hydrocarbons that contain 2 or more benzene rings, each pair of rings sharing 2 adjacent carbon atoms. Naphthalene shares 2 adjacent carbon atoms, 2 benzene rings together. Naphthalene, common component of mothballs. Anthracene has 3 benzene rings in a row, each sharing 2 carbon and hydrogens, 2 of them. Phenanthrene is also 3 benzene rings, but notice the position has changed. Instead of side by side in a linear fashion, that 3rd benzene is up. And we get larger and larger structures from there. Benzoapyrene, a 1, 2, 3, 4, 5 benzene ring structure. There is a topic in your book on page 387 that talks about polynuclear aromatics and smoking, seeing that these are major components of carcinogens. You know, benzene is actually quite a carcinogen as well. We used to have benzene in the chemistry lab until we realized through years of just data that it causes long-term liver damage and cancer. Benzene not only is poison if it's ingested in the liquid form, but even its vapor is toxic. It can be absorbed either by breathing it or even just absorbed through the skin by just handling it in a chemistry lab. So we have since removed it from all college and high school chemistry labs. And in the industry, it's still commonly used, but boy, people are sure careful in always wearing proper equipment in terms of rubber gloves, safety gloves, so forth. You cannot even get skin exposure because it will absorb through your skin. So they have come a long way in the safety of handling such as, just an important industrial solvent such as benzene. When we pick up in the next lesson, we'll talk about the reactions that are characteristic of benzene and its derivatives.